Hi, my name is Zhuowen Zhang, Ben. I'm a PhD student at the University of Chicago. In this talk, I will talk about the impact of property covariance on galaxy cluster weak lensing mass calibration. In the galaxy cluster optical weak lensing regime, there are two main cluster observables that we work with. One is the cluster lensing signal. This is the excess shear measurement of source galaxies when lensed by galaxy clusters. This measurement for that is denoted as delta sigma, which is the excess surface density around the center of the cluster. In real data, we use the excess shear measurement of the galaxies as a proxy. In simulations, we have access to the dark matter particles, and we directly compute the excess surface density of the dark matter particles. The second observable is a quantity called richness. To first order, this is a number count of the galaxies inside the galaxy cluster. Here, you have an algorithm called RedMapper that detects a probabilistic distribution of galaxies inside a radius approximating the gravitationally bound radius of the cluster. That's denoted by this letter lambda, and this computes the probabilistic summation of all of the red sequence galaxies inside the gravitationally bound radius of the cluster. Armed with these two measurements, we can perform cluster cosmology. The two cosmological parameters that we can detect with galaxy clusters are omega n and sigma 8. As these parameters are sensitive to the amplitude of the halo mass function, because we don't have direct access to the individual mass information of clusters, we have to construct a mass to observable scaling relation. The observable that we have here is the richness quantity I described. So by constructing a richness to weak lensing mass relation, and then folding that into a weak lensing mass to real mass, true mass information, we can use observational data to infer the real halo mass function and use that to construct cluster cosmology with galaxy clusters. There are a lot of systematic biases that we have to address with cluster observables. To name a few, these are shear measurements, photometric redshift error, triaxiality, miscentering, and so forth. According to a paper by Tom McClintock et al., systematics and statistical uncertainties in the dark energy survey year 1 footprint are on par with each other. Statistical uncertainty is mostly dominated by the shape noise of galaxies, which, as you increase the number density of galaxies, will decrease. In near future surveys, such as the Vera Rubin survey, as we increase the number of galaxies detected by order of magnitude, the shape noise will drop by an order of magnitude. And hence, in near future surveys, systematics will soon dominate statistical noise. It's therefore very important for us to model accurately all of these systematics. Currently, there is one unconstrained systematic that we address in this project. This is the correlated scatter between these two weak lensing observables, delta sigma, the weak lensing signal, and the log of the richness. This is folded into the scaling relation. You can think of it as a first-order Taylor expansion term to the scaling relation that was left unconstrained by previous studies. The goal of this project then is to use n-body simulation. We use the multi-dark Planck 2 simulation with a SAGE semi-analytic galaxy model to set informative priors of this covariance and describe its impact on the scaling relation and the mass measurements. Here, I will first introduce the data vector. To build a covariance, we need two ingredients, richness and delta sigma. Richness is here defined as the total number of galaxies enclosed inside a gravitationally bound radius of the cluster. We play with different radius definitions, R200C, R virial, and a constant 1 megaparsec radius. What we find is that different radius definitions gives us different number counts and statistically changes the richness mass scaling relation. We use R200C as our final model as it best matches the literature using observational data. However, I will note that in a future slide that even though it does change the richness count, it plays a negligible impact on the covariance itself. The second ingredient is the delta sigma lensing signal measurements. This is directly computed from dark matter particles. We span mass and redshift ranges spanning optical cluster ranges. Here plotted is a sample mass and redshift bin showing the measurements of delta sigma with theoretical predictions using different mass and concentration relations and halo bias models. We find that these models are consistent with our measurements, but the error bars are too big for us to distinguish between different models. In the last part of the data vector, I introduce an algorithm called kernel local linear regression that conditions on the mass. So here, when we take the delta sigma measurements, in the scatter of the delta sigma when building the covariance, instead of taking the scatter across a global mean, we take it on the local mean with mass being the independent observable. In the lower left panel, you see the difference in the scatter when you take it across the global mean versus the local mean at that particular mass. This algorithm effectively conditions on the mass. It removes the mass dependency and also reduces the scatter. We apply the same algorithm to construct the mass observable mass richness relation. Having constructed the data vector, we now make measurements on the covariance, conditioned on mass and redshift. Here, across different mass and redshift bins spanning the full range of cluster optical surveys, we find this universal shape of a null covariance at small scales and a null covariance at large scales. Because of the universality of the shape, we can model it as an offset error function that consists of 4 parameters. Here, I'll talk about these parameters and how they evolve with mass and redshift in the next slide. So these 4 parameters, they are gamma, the horizontal offset, tau, horizontal scale, g, the vertical offset, s, the vertical scale. Specifically, g equals to -1 means that the covariance goes to 0 isotopically at large scales. We first explore the impact that the radius definition has on the covariance parameters. As I had discussed, different radius definition changes the mass richness relation. However, they do not make a strong impact on the parameters for the covariance. In most cases, g is consistent with -1, meaning that the covariance goes to 0 isotopically at large scales. However, we do find a strong mass and redshift dependency when we bin the clusters by their peak height. Here in the plot shown to the left, you can see visually that the size of the covariance changes significantly with the peak height. Looking at the parameter space in the right-hand side, we find that tau, gamma, and g are roughly consistent across different peak heights. G in most bins are consistent with -1. However, we find a strong dependence between S, the scale of the covariance, with the peak height that we model as a log linear relation. This shows the size of the covariance covariance is largely dependent on the time formation history of the cluster. Next, we model the richness, we model the scaling relation, the impact of the scaling relation of the covariance. Here, the equations give us the first and second order dependence, the impact of the scaling relation that the covariance has, where gamma 1 and gamma 2 are respectively the first and second order Taylor expansions of the halo mass function, and alpha of n is the slope of the mass richness relation, which is roughly equal to 1. What we find here in the brown lines, the first order expansion, is that there is roughly a 1% bias on the stacked delta sigma relation at small scales. We find that different models of the halo mass function, or taking into the second order, these corrections are subdominant to the first order expansion itself, and hence our error measurements converge. When we propagate this correction of delta sigma into a mass bias by propagating it onto a change in the posterior of the NFW profile, we find that it propagates into a 2 to 3% mass bias. As I had alluded to in a previous paper by Tom McClintock, systematic uncertainty is on par with statistical ones. As you can see in the list of systematic uncertainties, most of them are at a percent level. Here we find this uncorrelated scatter contributes to 2 to 3% mass bias, and hence it's one of the most important and unconstrained systematics for us to model going forward. Next, I will talk about the dependence of the covariance on secondary Hall parameters. Here, we model richness and delta sigma as a multilinear function of the secondary parameters, where beta is a vector of the slopes, and pi is a vector of all of the secondary dependence parameters, which includes the mass accretion rate, half mass scale factor, concentration, kinetic to potential energy ratio, and miscentering offset. Using this model, this covariance takes on the form of this matrix equation as given by this red box. In a recent paper, Shin and Diemer quantified the correlation of secondary parameters as the covariance between pi and pi. So our contribution in this project is the quantification of the slopes. Beta of tau is the slope for the delta sigma, and beta of n is the partial slopes for the richness on secondary level parameters. By using this formalism, we can deconstruct the covariance as a summation of the individual components coming from each one of these secondary parameters as shown in the equation given here. In this plot, the blue error bars are the total covariance measurements that we saw previously. The thin dashed lines, different colors, give you the contribution coming from each one of the secondary components. By removing the contribution coming from each component, we get the black lines, which gives us the remaining term. We find that the black lines are all consistent with 0, meaning that these set of secondary parameters fully quantify the physical origin of the covariance. We find that all secondary parameters, they contribute to the covariance, and hence there is no dominant secondary parameter to choose from, as all of them are noisy and biased indicators of the time formation history of the cluster. Lastly, we compare our work to other works. Heidi Wu, using a buzzard simulation, compared the red mapper selected cluster. Red mapper is an optical cluster finder versus clusters selected by their true mass, and found a positive bias when comparing the ratio. Similarly, Tsuneyama used the cylinder halo occupation density to mimic the results of the red mapper, and she found that comparing the delta sigma observed versus delta sigma true gives us equally this positive bias. Song Huang, using HSC data, compared the red mapper selected clusters versus Chimera, which is an outer stellar mass proxy for the total mass of the cluster, which is less sensitive to projection effects. And what they found is that there's a boosting in delta sigma when selected by red mapper. It is therefore believed that this positive correlation that these other works find is when you adopt a more realistic cluster finder, such as red mapper, that takes into account projection effects. Here in this project, as mentioned, as we're encircling clusters inside a 3D radius instead of a 2D radius, we are immune from projection effects. And hence the difference between our work, where we're showing a negative bias, versus other works where they're showing a positive bias, is likely due to projection effects. And hence, by comparing the difference, we can quantify the net effect of projection effects. The takeaways from this project are, we find the negative covariance at small scales and the null covariance at large scales between weak lensing observables. This folds into a mass bias of 2 to 3% in most bins, and this is an important systematic that needs to be modeled. We show by the dependence of the covariance with the peak height that it suggests that there is a time formation history origin of the size of the covariance. As to why the covariance is negative, we explain it by decomposing it into its dependence on second order parameters, and we physically we explain fully the physical origin of this negative covariance that we're getting. We show that the difference between that our work and others that show a positive covariance is likely due to projection effects. That is all for my talk. Thank you for your time.